One of the biggest challenges theoretical physicists face today is explaining gravity, specifically creating a model that can explain both the grand and the small without violating any laws of physics. Black holes, as expected, violate these laws on the daily. Hi, I'm Seti, I'm a PhD student in astrophysics, and today we're going to be covering the black hole information paradox. Last time we covered the now solved faint young sun paradox, but today we're going to be covering a paradox that hasn't yet been solved. Or maybe it has. Some say it has, some say it hasn't. The jury's still out on this one. The black hole information paradox is the most challenging paradox that I'm going to be explaining in this mini-series. So a lot of the physics that it's tackling is very new and shiny. So I'm going to have to cover a little bit of ground concerning entropy and information. Entropy is usually described as the measurement of a system's disorder or randomness, or its inability to have work done within the system or on the system. And I don't quite like the disorder or randomness aspects of the explanation, although I do understand where it comes from. Rather, the inability to do work done is a lot more clearer. So for example, say you have a block of ice, on top of it some hot water. The entropy of that system is relatively low for now, but systems like this like to stay in equilibrium to be all balanced out. In this case, that means that the water is going to cool down and the ice is going to heat up, eventually ending up with just a lot of water all with the same semi-cold temperature. But once the whole system has reached the same temperature, all the particles have roughly the same energy, and no more work done can be done on the ice, which is now water, of course. So the entropy has increased up to its maximum amount. Entropy always increases or stays the same, which is why you can never get water turning back into ice, for example, in this way. Entropy, temperature, enthalpy, these are all state variables, which means you can use these alone to describe the state of something in equilibrium. You can make an expression using these variables, which is called a state function, and that state function will tell us the state of that system when it's in equilibrium. Now that all of the basics are covered, let's actually get back to the paradox. Anything going into a black hole is in some kind of state. It has information on its entropy, temperature, for example. So we can measure that information before it reaches the event horizon and enters the black hole. But once it crosses that event horizon, that information is gone to us. So provided the laws of thermodynamics are still working, the information is still there, we just can't see it. In fact, the only three properties we can see of a black hole are its mass, its charge, and its angular momentum. And all of these properties distort space-time around a black hole in a very unique way, such as frame dragging, for example, in a spinning black hole. This is the no-hair theorem, and it arises because the event horizon specifically marks the distance from the singularity of the black hole, where the escape velocity is the speed of light. So once something goes past that point, the light can't actually escape and come back to us, giving us that information. Or so we thought. The reason we can now challenge this is thanks to Birkenstein-Hawking radiation, which arose with the combination of quantum field theory and general relativity. Birkenstein-Hawking radiation is virtual radiation, whether that be light, photons, or neutrinos and antineutrinos that have spontaneously appeared and escaped the pull of a black hole. Virtual particles appear all the time and disappear all the time. They're basically a matter-antimatter pair, so in terms of charge, mass, angular momentum, everything, all of that gets conserved. It's just a little quirk of quantum mechanics. But if one pair is created on the event horizon where one is on each side, one of them has to, of course, fall into the singularity. The other one has the chance to escape and take some of the black hole's energy and mass with it. Now, the problem is, when this radiation is emitted from the black hole, its properties are only dependent on mass, charge, and angular momentum. It is not dependent on any of the other information that has fallen into the black hole, which means that all that temperature, that enthalpy, entropy that we were talking about is basically gone. Those state variables don't come into play whatsoever. Now, if the black hole stopped feeding and all that Birkenstein-Hawking radiation just continued to be emitted and take away all the mass and energy from that black hole, the black hole will eventually disintegrate. It's using up all of the mass that it's captured, but only the mass, charge, and angular momentum. All the other information, so the entropy, the enthalpy, and temperature and stuff, that information isn't getting used and is kind of just disappearing. The solution to this paradox is not yet known, but some claim it has been solved. Ideas as to where this information has gone include the Bekenstein-Hawking radiation, so perhaps there is an additional extra factor that we haven't accounted for, which is, likely. It's a bit like how, I guess, Mercury, its orbit has this little precession that Newtonian mechanics didn't really account for. But then came along Mileva-Maric with general relativity, and we were able to add that additional precession factor. It could just be that the physics hasn't developed yet, which is entirely possible. Perhaps maybe when the black hole has radiated away as much as it can, it ends with one big burst of energy, and that explosion includes all of that extra information. Who knows? The truth is, we really don't know, and it will take much longer than the age of the universe for a black hole to completely evaporate for us to actually see the end results of complete disintegration, so we'll probably never know from an observational perspective. But yeah, that wraps up the black hole information paradox. Thank you very much for watching. It was a really insightful paradox for me to learn about, and I hope you found that as well. I'll see you in 2 days' time for part 5.